Hi everyone, this is Dr. J. Ravindranath Reddy, working as Assistant Professor of Mathematics in MLR Institute of Technology, Hyderabad. So in this, we are discussing numerical methods and integral transform course. In that course, we are discussing the numerical solution of ordinary differential equations. And the method what we are going to discuss in this video is modified Euler's method. In the previous videos, we have seen how to find out the numerical solution of ordinary differential equations by using Taylor series method and Euler's method. Now in this video, we are going to discuss how to find out the numerical solution of ordinary differential equations with modified Euler's method. And we'll take some examples and we'll see how to solve the differential equations by using modified Euler's method. So first we'll see the working procedure, how we have to follow step by step in order to get the numerical solution using modified Euler's method. So consider the differential equation. As we said, we are going to discuss how to find out the solution using these numerical methods only for the first order differential equations. So the first order differential equation we have considered the standard form is dy by dx is equal to f of x comma y. So along with this differential equation, we have to get some initial condition. This is the standard form of that initial condition, that is y of x naught is equal to y naught. Now for this differential equation, at this initial condition, we have to find out the numerical solution by using modified Euler's method. So first we'll see how to get this. Now our question is, I want to find out the value of y. That means the solution for this differential equation at x is equal to x1. So how we will get this x1 value, that is x naught plus h. Now for this, first what we have to do is, we have to take the help of Euler's method. And by using that Euler's method, first we have to find out the rough estimation of this y1. So that rough estimation of this y1 we will consider as the initial approximation of y1. So whenever we want to apply this modified Euler's method, first we have to take the help of Euler's method, and by using that Euler's method, we have to find out the y1 value. That y1 value we have to consider as the initial approximation. And by using this initial approximation, we are going to find out the more accurate value of this y1 by using modified Euler's method. So this is the formula to find out y1 by using Euler's method. So whatever the value we get for y1, that we will consider as the initial approximation. So y1 power 0, this indicates the initial approximation of y1. So use this formula, find out this initial approximation of y1. Now we have to take the help of this initial approximation of y1 to get more accurate value for y1. So for this we are using modified Euler's method. So the modified Euler's method he has given us. So this is the standard formula to find out the solution by using modified Euler's method. So we have to take the first approximation of y1 first approximation, y1 second approximation of y1, and the third approximation of y1. So like this we have to find out the approximations of y1. So at a certain stage, the present approximation value will coincide with the previous approximation value. So whenever the present approximation coincides with the previous approximations, then we can stop our approximations and we can consider that value as our final value of y1. And similarly, if you want to find out the value of y2, then you consider x1 and y1 as initial values, and whatever the formulas we have taken, so you replace that y0 with y1 and x0 with x1 to get the value of y2. Here also you follow the same procedure. First find out the initial approximation of y2 using that Euler's method, and then apply modified Euler's method in order to get the more accurate value for y2. And this we have to follow according to the values of x he has given, where we have to find out the solution for the given differential equation. So this is the formula you will get to find out the first approximation of y1. So similarly, second approximation of y1. So whatever the approximation we get in the previous approximation, we have to use that previous approximation in the present approximation value. Suppose if you are going to find out the second approximation of y1, so while you are finding the second approximation of y1, so our previous approximation of y1 is first approximation. We have to use this first approximation of y1 to find out the second approximation of y1. So similarly, this is our standard formula to find out the approximations of y1. So whenever if you want to stop this, present approximation has to coincide with the previous approximation, and we have to stop that in that case. So if two successive values, suppose kth approximation of y1 and ka plus 1th approximation of y1 are sufficiently close to each other, then we can consider, we can take that value y1 is equal to, we can consider that a common value as the y1 value. Okay. So similarly, we have to proceed the same procedure for to find out the value of y2 and to find out the value of y3 and so on. So now let us take one example how we can find out this solution for this differential equation by using this modified Euler's method. So using modified Euler's method, find the approximate value of y when x is equal to 0.3, taking h is equal to 0.1. Given that dy by dx is equal to x plus y, along with the initial condition y of 0 equal to 1. So this is the differential equation, and with this initial condition, we have to find out the solution for this at x is equal to 0.3. But he has given one additional condition that the step length, that means the difference between the values of x, must be 0.1. So you compare this differential equation and the initial condition, you will get x naught is equal to 0, and here x value he has given as 0.3. Now this difference must coincide with the h value. So here the difference between x naught and x is 0.3 and our h value is 0.1. So these two are not equal. So now what we have to do is, we have to divide this interval into subintervals whose difference is equal to 0.1 by taking the help of this h value here. So now we'll see how to construct this. Now this is the given differential equation with the initial condition. So now as we discussed, now we are going to divide the interval 0, 0.3 into subintervals. So you consider this, whatever the initial condition he has given, you replace that initial condition of x with x naught, and its corresponding y value is y naught. Now this is the value he has given in our table, x in our problem, x is equal to 0.3. So the difference between 0 and 0.3 is not equal to 0.1. So because of that reason, we are dividing 0, 0.3 into some subintervals. The length of that subinterval must be equal to 0.1. Now I have taken the initial value. So now I want to take x1 value here. So this is very simple here. So in order to get this x1 value, take its previous value, that is x naught, and for this x naught you add h value. So x naught is 0, h is 0.1. So 0 plus 0.1 we will get 0.1. This we have to consider as x1 value, and go for the next x2. Similarly, take its previous value, that is x1, plus add that h value. So 0.1 plus 0.1 you will get 0.2. And similarly, you find out the value of x3 also. Now if you take the difference between these two, this value is equal to h. If you take the difference between these two, 0.1 and 0.2, which is equal to h value, and similarly if you take 0.2 and 0.3, this difference is also equal to 0.1. So according to this h value, we have to, the difference between the values of x must be equal to the h value. Now, so if you consider this 0.1 as x1, whatever the value we get for y, we have to consider that y value as y1. And similarly for x2, its corresponding y value is represented with y2. For x3, its corresponding y value is represented with y3. Now, our task is we have to find out y1, y2, y3 by using this modified Euler's method. So once if we complete this y1, y2, y3, then we can complete our problem here. Now we'll start here. So now you complete this differential equation with the standard form. Just now we have seen that standard form. Dy by dx is equal to f of x comma y. You compare these two and get the value of f of x comma y. So this is our f of x comma y is equal to x plus y. And compare this with the standard initial condition, which is given as y of x naught is equal to y naught. You compare this, in place of x naught here we are having 0, so x naught is equal to 0, and in place of y naught here we are having 1, so you consider y naught is equal to 1. So this is the way how we can get f of x comma y value, function value, x naught value and y naught value here. So now according to our modified Euler's procedure, first we have to find out the, so now my task is I want to get the value of y1. So in order to get the accurate value for y1, first I will take the rough estimation of y1 by using Euler's method. So now take the h value. So now our task is, already we said that we are going to find out the value of y1. So y1 is nothing but at x is equal to x1, whatever the value we get for y, that will be considered as y1. So y1 is equal to y of x1, which is equal to y of x1. x1 is 0.1. So we are going to find out this value here. So as we said earlier, we are using Euler's method. So whatever the value we get for y1, we will consider that as a initial approximation of y1. This is the formula we will use to find out initial approximation of y1. We know the value of y naught, replace. We know the value of h, replace that h value. And we know the function f of x comma y, in that replace x with x naught and y with y naught here, and calculate that. So you will get that initial approximation of y1 is equal to 1.1. Just substitute this. So here f of x, we have discussed at the beginning of the solution, we have taken that f of x comma y is equal to x plus y. So now we have to get the value of f of x naught comma y naught. So this can be written as x naught plus y naught. So replace x naught value. So this is x naught is 0 and y naught is 1. So 0 plus 1 is equal to 1. So into we have to multiply this value with 0.1. So you will get this initial approximation of y1 is equal to 1.1. Now by using this initial approximation, we are going to apply the modified Euler's method, and we are going to get the first approximation of y1, second approximation of y1, third approximation of y1. So now the formula of Euler's modified Euler's method is given by, so this is the standard formula we are having for modified Euler's. Now from this formula I want to get the value of first approximation of y1. So here we want y1, and in the numerator here in place of y we want the 1. So substitute I is equal to 1 and k is equal to 0 here. Then we can get our first approximation of y1. So after substituting, so put I is equal to 1 and k is equal to 0 in this equation, we will get the standard formula to find out the first approximation of y1 here. Now replace these values here. So y0 and h, that is fixed throughout the problem. H is 0.1 by 2 f of x0 comma y0 plus f of x1 comma initial approximation of y1. So replace these values here, all the values. So simplify this, you will get the first approximation of y1 is equal to 1.11. This is the first approximation of y1. Now similarly, we will go for the second approximation of y1. So in order to get the second approximation of y1, keep k is equal to 0 and substitute I is equal to 2 here. Then we can get our standard formula to find out the second approximation here. So this is the formula after replacing k is equal to 0 and I equal to 2 in equation 1. Now substitute these values one by one here. y0, in place of y0 I have taken 1, and h we got 0.1 by 2, and f of 0 comma 1, x0 is 0 and y0 is 1, and x1 we have taken as 0.1, and we got its previous approximation of y1 is 1.11. Now simplify this, we will get our second approximation of y1. So now if you want to stop the problem, you compare the values of first approximation of y1 and second approximation of y1. So if these values are coincidence, then we can stop. Otherwise, we have to go to the third approximation here. So I want to go for the third approximation because the first approximation we got to only 1.11. So here we got 1.1105. So minimum 3 to 4 digits has to coincide here after decimal point. So this is the formula. So replace I is equal to 3 in equation 1. We will get the third approximation by substituting k is equal to 0 as this. So once again you substitute all the values here. So here we will get third approximation of y1 is equal to 1.1105. So now before going to for the next approximation, you just coincide the third approximation value and second approximation. You just compare the two approximations. In the two approximations, if the value is not coincident, then we can go for the fourth approximation. Now here we got the second approximation as 1.1105. The third approximation also we got 1.1105. In both approximations we got the same values here. So whenever we are having this type of situation, then no need to go for the next approximation. So whatever the value we got, common value we got in both approximations, we'll consider that value as y1. So this is because of this reason. This second approximation of y1 is equal to third approximation of y1. Both are same. So we can consider that common value as y1 value here. So finally we got y1 is equal to 1.1105. So this is the way how we can find out this y1 value. Follow the same procedure to find out y2 and y3 here. Now our second step is I want to go for the y2. So y2 is nothing but we getting the value at x is equal to x2. Our x2 value is 0.2. So whenever we want to find out this y2 value, so we have to consider x1 and y1 as the initial values. So this is the point what we are discussing from starting of from the first method onwards. So whenever we are going to find out this y2 value by using any method, we have to consider x1 and y1 as the initial values. And similarly, whenever we are going to find out this y1 value, we have to consider x0 and y0 as the initial values. So take k is equal to 1 in the standard formula and substitute I is equal k equal to 1. We will get this is the formula you will get for modified Euler's method. Follow the same procedure. First you find out the initial approximation of y2 by using that modified by using Euler's method. So this is the formula to find out the first approximation of y2. So can be calculated by using this initial approximation is to be calculated by using Euler's method. So this is the formula to find out the initial approximation of y2 using Euler's method. Substitute these values, you will get initial approximation of y2 is equal to 1.2316. Now use this initial value of y2 in the modified Euler's method and find out the approximations here. So we have the formula to find out this first approximation. This is our standard formula to find out the first approximation of y2. So substitute this y1 value, h value, x1, y1, x2, y initial approximation of y2 in this formula. So we'll get these are the values. So finally we'll get the first approximation of y2 is equal to 1.2426. Now we have to go for the second approximation. So this is the formula you will use for the second approximation by substituting I is equal to 2 here. So here also you substitute the values. So in place of y1 you take y1 value what we got, and h is equal to 0.1. Find out f of x1 comma y1, and find out f of x2 comma first approximation of y2. Use this value here and replace and simplify, you will get our second approximation. So once if you observe this second approximation and the first approximation, after decimal point only 2 digits are coincidence. The third digit is third and fourth digit is not coincidence, so you go for the next approximation. So third approximation, you take this by substituting I is equal to 3 in the standard formula and substitute the values. You will get third approximation of y2 is equal to 1.2432. So now this approximation value is equal to the second approximation value. So because of this reason, so second approximation of y2 is equal to the third approximation of y2. So you consider this common value as our final value of y2. So like this you find out. Similarly, you find out that y3 value at x is equal to 0.3. You will get these values in the standard formula by substituting k is equal to 2. And then I is equal to 1. This is the formula we will use to find out the first approximation of y3. Before that, we have to find out the initial approximation of y3 by using Euler's method. So this is by using this formula, we got the initial approximation of y3 is equal to 1.3875. Use this to find out the first approximation of y3 using modified Euler's method. So use this formula to find out first approximation of y3 and simplify the values. Follow the same procedure what we have followed in step 1 and step 2. You will get the first approximation of y3 which is equal to 1.3997. And similarly go for the next second approximation of y3. Substitute the values and simplify. You will get second approximation of y3 is equal to 1.4003. So this value and this value is not coincidence. So definitely we have to go for the next approximation. So third approximation of y3, we got this value. So 1.4004. So in the previous approximation, we got this 1.4003, and here we got 1.4004. So up to 3 decimals are coincidence. So there is a small change in the fourth digit. So then we can consider that approximately equal. Otherwise, if you want, you can go for this next one also. Fourth approximation. If you want, we can stop. Otherwise, if you want to get more accurate value, same values in both approximations, then you can go for the fourth approximation. In the fourth approximation, all 4 digits are coincidence. So 1.4004 in the fourth approximation also we got the same value. So third approximation value and the fourth approximation values are similar, equal. Then we can consider that value as the y3 value here. So this is the way how we can find out this y3 value by using modified Euler's method. So once again, I'll repeat the procedure here. So if you want to find out y1 value by using modified Euler's, first we have to find out the initial approximation of y1 using Euler's method. And by using this initial approximation, use the modified Euler's method to find out the first approximation of y1 and the second approximation of y1 and the third approximation of y1 and so on. At a certain approximation, the present approximation value is equal to its previous approximation value. So whenever the present and the previous approximation both values are equal, then we can stop and we can consider that value as our final value of y1. The same process will be repeated to find out y2 and y3 here. So this is the procedure of modified Euler's method. So in this video, we have seen how to find out the numerical solution of ordinary differential equation by using modified Euler's method. So in the next video, we'll go for the same numerical solution of ordinary differential equation, but with a different method, that is Runge-Kutta method. So by using this Runge-Kutta method, we'll see how to find out the numerical solution of this ordinary differential equation. So this is our last method to find out the numerical solution of ordinary differential equation in our syllabus. Thank you.